All right, so we're starting simple harmonic motion today. That's our next unit, okay? Now, with simple harmonic motion, it's kind of interesting because we're going to take some things that we already know from a bunch of other topics. So we're going to take things from like forces, and we're going to take things from circular motion. It's kind of cool how we can put them together and we get simple harmonic motion. Now, simple harmonic motion is really, really simple in terms of what it is, okay? So for simple harmonic motion, it's just back and forth motion. And that back and forth motion occurs because there's some sort of restoring force. All right, so when we talk restoring force, we're talking about something that wants to pull the object back towards its equilibrium point. Does that make sense? All right. So we could talk about something that's on a spring. All right. We could talk about something that's on a pendulum. Okay. So if we're on a spring, right, right, our restoring force is that force of the spring pulling the thing back. So if we pulled the block this way, right, we're going to have a restoring force that's going to want to pull it here. Makes sense, right? We're just going to want to pull it back. And then once it gets past the equilibrium point, the spring's going to want to push it back towards the other way, right? Makes sense. Okay? And if we remember, we should remember that force because of a spring is equal to negative kx. Right, if this is our equilibrium point and this is the distance that we're going to pull it, right? It would be equal to F equals negative kx. We already know that. We learned that months ago. Okay? If we're talking about a pendulum, right, and we have it over here, and this is our equilibrium point, right, we're going to have components of the weight acting on this guy that are going to pull it back towards the equilibrium point on the pendulum. Right? Does that make sense? Right? And then it's going to swing this way, and the weight's going to want to pull it back, and that's what we're going to have this simple harmonic motion. Right? Is this back and forth type of motion. Because, right, and it occurs because there's a restoring force trying to pull it back towards its equilibrium point. Okay? And that's everything that has to really go into that in terms of, that's pretty much simple harmonic motion in a nutshell. I wish we could say that that's it, but it's not it. Yep.
So, like, the restoring force of the pendulum would be like gravity pulling it back towards...
Right. Right. Because you can look at, right, like this, and then you've got, if you look in line with that, you've got a component this way, and you've got a component that way. Okay? Awesome. So that's really what it is it's caused by this restoring force, but we're gonna get through a little bit of vocabulary to get where we need to be, all right? The first thing is an oscillation, okay? So when an oscillation is very, very simple, okay? It's one complete motion. Okay? That means it's one complete back and forth. Okay? So if we're talking about a pendulum here, going from here and then back would be one complete oscillation. Okay? If we're talking about the spring, right, going here and then coming back would be one complete oscillation. Okay? Simple. Makes sense, right? But it's very important when we start talking about waves and more about the mechanics of it is because we need to understand what an oscillation is. Okay? Good to go? All right. So previously, when we were in uniform circular motion, we talked about period, right? And what did we say period was? Okay, time to go around once?
Yeah.
We'll say that, time to go around once. So instead of saying going around once, what could we call it, the time for what, if we're talking about this, right? Right, time for one oscillation. So now the period is the time for one oscillation. Right, and that's in seconds. Okay, and we call it capital T. Okay. Make sense? Pretty simple, pretty good, right? Okay. We can also talk, instead of in terms of the time to go once, we could also talk about it in terms of this thing called frequency. Okay? And that's really, a lot of the times when you're in simple harmonic motion, they talk about frequency instead of periods. Okay? And frequency is just the number of oscillations in a second, or the number of cycles, which are the same thing. Okay? And we use the unit, the hertz. Okay? And that is like a script F when we talk frequency. Okay? And an example of frequency, these light bulbs, because they work on alternating current, they work at a frequency of 60 hertz. That means that alternating current is current that goes back and forth like this. It changes its direction. It's changing its direction. It's doing 60 complete cycles every second. So if you took like a high-speed camera and you shot it at 60 frames per second, they blink. All right, so period and frequency. You see that this is time for one cycle, and this is the number of cycles in 1 second. So they have an inverse relationship to each other. So period is 1 over the frequency. So frequency is 1 over the period. All right? Makes sense. It's simple. Okay? But this is going to be really important because there's going to be a lot of manipulation that goes on with period and frequency. Sometimes to make it look nicer, sometimes it just makes it life easier. And you'll see when we're going to do this big long derivation, you're going to see that it makes life a lot simpler if you have that. Okay? Now, this capital T, when we're talking waves in simple harmonic motion, it's a constant number. Okay? So we're calling it capital T. So we're going to have some equations where it's going to be like 2 pi, ft over t, something like this. This number is going to, we wouldn't have the f in there, I'm sorry. This number is going to be the same all the time. It's going to be like a constant number, and this is going to be the time that changes. Okay?
What letter is that?
This is t. So like lowercase t time. So time, and this is capital T period. Okay? So essentially, this would be like a ratio of the time where you are compared to the time for one cycle. Okay?
Tell you like distance of how far you went.
You can figure, yes, that's exactly what's going to happen. Okay?
What is
Yep.
that equal to?
This,
Yeah, that whole thing.
this whole thing, it's part of another equation that we're going to see in a few minutes. So don't worry about it. Yeah, I just wanted to write it down so you'd see what it is. Yep.
So because T can't change, is there like no acceleration?
The particle's going to accelerate, and it's going to be a function of the frequency or the period. Okay? Again, we'll see that in a second. Okay? Are we good? Okay. All right, so here's what I want to do. I want to figure out how can I predict the position of something in simple harmonic motion. All right? So I want to be able to say, all right, this is time equals 13 seconds. I want to know where the object is. All right? So if I've got a pendulum going like this, or I've got a weight on a spring bouncing back and forth, I want to know where is it at any time. Does that make sense? Okay? All right, so let's start with, let's say we've got a pendulum. Okay? And this is at position A. It's at its maximum. Okay? And then we let it go, and it cycles through these. Okay? Does that make sense? Makes sense, right? Pretty simple? Okay. So what I want to do is I want to graph it. Let's graph its position. Not too bad. Okay, so this would be, and this is your x versus time, okay?
Would it be X or delta T?
This is its position related to its time. Right. All right, so this A is different from this A. This would be like position A. This is its maximum amplitude. Okay, I labeled it kind of poorly. How about instead we call it 1? What's that? All right, so at point A, right, it's going to be at its maximum, correct? Okay, so it's going to start up here, and as it comes down, its position goes to 0, right? So it's going to come down to 0. So this would be at position 1, right? This would be position 2, and then it goes back to, now it's negative amplitude, right? It's negative maximum amplitude because it's on the other side. So we could put the point, I don't know, somewhere like right here. And this would be 0.3, right? But then it's going to come back to 0, right? Which would be 0.2 again. And then it goes back up to 0.1. What is that? Oh, it might be a cosine curve, right. So this is kind of cool. Simple harmonic motion, no matter if it's a pendulum, if it's a spring bouncing on a thing, we're going to do something else later on which shows something different, right? It is a sinusoidal motion. I can't say it. No, sinusoidal. It means it follows a sine curve, right?
Like vegetarian.
Same idea. Trust me, you'll see in a second. All right? So, oh, okay, like that. Put the dotted line? Yeah, so that's just the equilibrium point, right?
That's like what the dotted line is too.
Yes. Yeah, so this is the maximum. This is the maximum amplitude on the other side. That's why we call it negative A. Okay?
One oscillation
Right. So we can call now its position, right? Its position as a function of time. Okay? Could we call it A, which is its maximum value, and we see that it's a cosine curve, cosine of theta. Now remember that theta is not the angle, it's the angular position. Does that make sense? So this is in radians. So when we're dealing with this equation right here, we're talking about simple harmonic motion, calculator needs to be in radians. Right, that's very important. Okay? So here's what I want to do. There's no t in here. There's no function of t. Yeah. We're saying that the equation is a function. There's no t. That's a problem, right? That's a problem.
Not really.
Okay, so here's what we're going to do. Let's start it very simple, just so we can see that this makes sense. When your theta is 0 radians, right? What is the cosine of 0 radians? Cosine of 0. It's 1. Does that give you the max amplitude?
Yeah.
Okay, down here, which is 1 over here, that would be what? Pi?
Yes.
That would be pi radians. What's the cosine of pi radians?
-1.
-1. Does that give you negative amplitude? There you go. So that's what we're doing here, all right?
So where's our T?
So here's how we get the t in there. Shh. Here's how we get the t in here. This would be your position, right? If we're talking about, let's go back to our circular motion or rotational motion. That is 2 pi, right? 2 pi radians, but we want to make it a function of the time. So it would be your time divided by your period. So now you've got the ratio of your time compared to your period, right? Seconds and seconds, they cancel out, so we're left with radians again. Okay? Does that make sense? So, but I want to make it neater. This is kind of like, in the world of physics and science and stuff, they like to make things elegant, right? So let's make it elegant. So, what we can say is, we can say the position right, is equal to a cosine of 2 pi. Now instead of, that's 1 over t, right? What's 1 over t equal to? Frequency. So frequency times time. I'm sorry I squished it in there. Okay? So if I want to find out what the position of an object is anywhere in simple harmonic motion, it's a cosine, right? The amplitude times the cosine of 2 pi times the frequency times the time. So all I need to know is that you can find the frequency. We'll learn how to read these graphs to determine what the frequency is, right? All I need to know is the time, right? And you can read the amplitude off of a graph. Okay? That makes sense? Okay? We're going to come back to this in a little while, where I'm going to show you another way to get this, and then we're going to, from this, figure out how can we find the speed, how can we find the acceleration, and then what I'm going to do for you kids that are in AB or BC Calc, it's actually going to be a whole heck of a lot easier in the end. Okay? So, all right.